recognition by Aruna Rajan, who's currently associated as an advisor and volunteer with Magasool. This is a non-profit initiative to make agriculture viable for small and marginal farmers. Sorry, can you all hear me?
Yes,
okay.
Radhika.
All right. So this next talk, Building ML for Internet Scale by Aruna Rajan. She's an advisor and volunteer with Magasool. That's a non-profit initiative to make agriculture viable for small and marginal farmers. But she's here to talk with us. Yeah, Aruna.
I hope the PDF is
talk to women in data sciences. Very excited to hear all the awesome talks this morning, and thank you to Shrujana and Professor Sanghamitra for a very insightful talk. I don't want to take too much time. This is meant to be a lightning talk. I just want to explain how voice search works, and just to leave you with a flavor of how deep learning has made some progress that makes this problem interesting, and how to scale complicate this problem. So I'll leave you with key takeaways on most of the slides and try not to get too deep into the maths or the other technical elements. Can we go to the next slide, please? So to start with, the problem statement that we are going to talk about for the next 10 minutes is a speech recognition system. It basically takes in any voice input and then converts that into a string of text. And now let's fix the language in English for the sake of this discussion. And there are several use cases that you could find for this type of a recognition system. It could be something where you're reading out a book or reading out a conversation, or one where you're having a conversation, or one where you're trying to issue some kind of command and get a program to do something for you, more like your speech assistants of today. So for the sake of this flash talk, I will talk about speech assistants that work on a command control sort of mode. Next slide. So the ideal state that we want to go to in the long term for speech recognition is really one where you're able to say whatever you're saying as raw input to a black box, and that's how we think of neural networks. You're able to get out the plain text of whatever you're saying, which is, let's say you just said hello, and there is a magical neural network that can transcribe this as HELLO. That's sort of the end state for voice recognition systems. And we're not there yet. There are plenty of these parts that are done as a combination of networks. Deep learning is now replacing several of these individual pieces. And what I want to leave you with in this talk is which of those pieces have been replaced, what's left to do, and how does scale complicate this. So let's go to the next slide. Let me start by telling you how a traditional speech recognition pipeline works. So when you are speaking, let's say you're saying hello, and the first thing to do is to convert this into a feature representation like we do for all ML problems. And then we have a decoder that has really three pieces to it. One is a pronunciation model. So in a Bayesian framework, that Lavanya just talked about in the morning, you can think about this as what is the probability of having a particular utterance when you meant to convey a certain string of words. And that is broken down into three components: pronunciation model for what are the different ways to pronounce a word, an acoustic model for what are the different phonemes that an acoustic signal is associated with, and a language model for really how often do you expect a certain word to come up, and what is the probability that you're hearing a certain word that is common to a language. And the advantage of these traditional pipelines is that each of these three things can be independently updated. So if you have a new pronunciation for a word, let's say you want to extend an English voice recognition system to understand Indian accents, then it is about just updating your library for the pronunciation model. Similarly, if you have new types of acoustic characteristics, you have different mics, different devices, and different acoustics, then you are updating a very different model. So this has its pros and its cons. As many of you might know, when you are able to update simultaneously, you also lose a little bit of debuggability. So whenever you encounter a new situation in which your pipeline throws really bad results, then it's very hard to tell which of these models are the problem and where should you really be focusing on to make the improvement. And it becomes very expensive to try and do all three things, or try and process speech and sample speech in a different way so that you get more accurate answers. So now I'll take you to a deep learning picture of the same thing on the next slide. So let's try and formulate this the deep learning way. So our goal is that we want to start with a speech signal shown in the diagram as X, which is the input vector, and you want to go to a word Y, which is in this case hello, and that is a voice transcript of someone saying hello. So one of the things that speech recognition starts with is a spectrogram, which is basically how much energy do each of the frequencies in your wave contain. So a representation of that is what one calls a spectrogram, and you start from that, and then you try and replace the acoustic model, which is looking at what are the possible phonemes, or what are the possible word parts that that could be the user's intent to convey, given whatever they've just said. So replacing that traditional speech recognition pipeline has led, with deep learning, has led to more than a 20% increase in accuracy. So plenty of what you're able to see the likes of Alexa and Google Assistant do today are really because of shifting from HMM, or a conventional model of acoustic pipeline, to a more deep learning based model, which really works on recurrent neural networks. I won't go into the depth of those, but sort of leave you with a feeling of what they're doing. And the reason this problem formulation is hard is that different people say hello in different ways. So you're no longer like if you're trying to do language learning from text, then you have a certain way in which words are represented, and that is a fixed length. So hello is a word of a fixed length. Whereas in acoustics, really different people might say hello in different ways. Somebody might say hello, somebody might say hello, and their mic characteristics, their ways of stressing on symbols, and their accents will really lead to a different length of your input vector. So the first problem really in deep learning is how do you transform this so that you have a fixed length vector for a given word. On the next slide. So there are sort of three steps to do this. The first thing is that we use a fixed grammar, which is, we say that we're going to stick with phonemes, or we stick with graphemes. Let's, for the purpose of this talk, just talk about phonemes. These are basically pronunciation units for a word. And what we then do is we map the input to output neurons that encode these phonemes. And then we try and make a map between these phonemes, which is called beta on the slide, to a word. And then what we do is we maximize the likelihood of finding a particular word under this model. So, sort of argmax of finding the word W, given that you will then increase your, you have maximum probability of seeing whatever utterance the user gave you. So in this particular formulation is called a connectionist temporal classification. What you are essentially trying to do is find the most likely word given the utterance. Next slide, please. So on the right, I'm listing out one possible way of doing this, which really is assuming that every utterance that you have is independent of the previous. This is obviously not a very tight assumption, but sometimes these assumptions sort of help formulate and help get ahead. So obviously, if I said her, then you know, the likelihood of saying la after that is different from if I had said ka. right? So, but without worrying about that, and by treating each of these utterances of phonemes as independent from each other, we get a formulation in which what you're trying to do is look at how possible is the word hello from the set of phonemes you land at. And that's represented on the left side. There are lots of standard algos to do this. If you're trying to build your own speech recognition system, you can look up what is called CTC, and then there are gradient methods that solve for CTC and which come out with your most likely set of phonemes given a word. And that's what you will get out of playing with the CTC based RNN. Moving to the next slide, I'm going to talk about the last part, which is really how do you figure out the word once you have a representation and once you have figured out the phonemes. And then the way that we do this in production today is really simple n-gram language models. And that is about we look at trigrams or bigrams. And then what you're basically saying is, what is the probability of this word occurring in this user's utterance? Just let's forget everything about the user for now, and let's just look at the fact that the language is English. So we're kind of learning from a corpora of what is the likelihood of somebody saying hello. And then there's other things of what is the likelihood of somebody starting with hello, and that's pretty high. Similarly, there are ways to adapt this to a particular user. So the more that models get adapted to a particular user's context, the more likely you are to predict what they are going to say next more accurately. So that's sort of the intuitive way of thinking about it. There are problems with this. There's a popular problem called the Tchaikovsky problem, which is really, if you've never heard this word and your corpora has never seen this word before used in this context, then it's going to be very hard to figure out what the word is, and you're likely going to make egregious errors. So plenty of you might have seen this happen with your voice assistants, that egregious errors pop up a lot. And that's one of the problems with any language at scale. It's really hard to tell what is a specific utterance, what is a commonly known word, and it's very difficult to use language models to sort of guess words. The last piece that I want to leave you with is what complicates this at scale. The first thing that complicates it at scale is that different users have different kinds of acoustics, and they're exposed to different noise. And the way that deep learning practitioners try to solve for this is really take synthesized noise, add it to their voice input, and try and retrain their networks to see what they land at, and keep trying to add more noisy variants of the same sort of utterances. The other thing is, this is huge computation. As you can imagine, if you have about even 1,000 users using a voice assistant app, and you are you're gathering data from them for 2 hours a day, you end up with a huge number of utterances, and it is computationally really complex. And today, the state-of-the-art papers use more than 64 GPUs to process about 1 million hours of speech. So that's the scale at which this compute happens. It's about 10 power 20 flops, which is really huge. It takes about 30 days on one Titan X core. So there is a new problem at scale of how do you simplify this compute? How can you get more out of your GPUs, and how can you really compute faster? And in that, there are techniques like mini batching, where you're trying to align utterances of similar length together and send them as one batch, and not have too much variance in the length of the utterances in a batch, so that you are optimally using compute. So there are many cool problems like this that kind of pop up when you're doing speech recognition. I just wanted to leave you with a flavor of those, and that's the end of my lightning, not so lightning talk.
That was definitely lightning. Thank you, Aruna, for that tech talk. So I expect people will have questions. Please put them down for Aruna and the other speakers into the Google Forms. So moving on, as data scientists, engineers, and leaders,